Okay, so I'm going to go over a sketch of the proof of this. I'm not calling this like a full proof because I am going to kind of gloss over some of the details here, but I want you to understand with a little more rigor where this comes from. Okay, so understanding this proof is really going to solidify, I think, the connection between a definite integral and the idea of differentiation, a derivative and an antiderivative. So here's what we want to prove. Okay, we want to prove that if you take the derivative of this accumulation function of the lowercase f, then what you get back is lowercase f. Okay. So first thing I want to do is let's let capital F be the function that is this accumulation function here. Sorry, mincing my words. I just want to give that function a name. Okay, so we're going to call it capital F. All right. So then what we're trying to do here is calculate capital F prime. Okay, let's go back to basics. Let's go back to the derivative. This is going to be a limit as delta x approaches 0 of capital F of x plus delta x minus capital F of x, and then all over delta x, right? So then what we can do is put that in terms of limits. I'm sorry, I misspoke. Put that in terms of integrals. That's what I meant to say. So let's use this capital F function. This is going to be the integral from, oh, hang on a second. Yeah, this is right. The integral from a up to x plus delta x of ft dt. So that's taking the x plus delta x and sticking it into this function. The place you put it is right here, right? You put it up in the upper limit of integration. So we have a up to x plus delta x. This is still f of t, right? Because this is just the function that we're accumulating under. And so you've got that integral minus the integral from a up to x of f of t dt. And then all over delta x. So let's draw a picture of what we're talking about here. Here's our function, y equals f of t. Okay. Here's our a, where we start. We're measuring from here. And then somewhere over here we've got x. And then somewhere a little further on, perhaps, is where we have x plus delta x. So what we're talking about doing is taking the integral, this part here, I'm going to start color coding. This part is the integral from a up to x plus delta x. So I'm going to outline that area from a up to x plus delta x. It's going to look like this, outlined in red. And then what we're doing is subtracting from that this integral, which is from a up to x. And that is going to take off the first part of it up to there. So we have left over, after subtracting, is just this area right here. So I can write this as the limit as delta x approaches 0 of just 1 over delta x, which is my division there, and then times the numerator, which is just that sliver. It's going to be from x up to x plus delta x, f of t dt. Okay, just that. Now, this part here, the top of this little segment is curved, potentially, right? Because this is the function y equals f of t. So this could be some curve. But what we can do is we can approximate that by a rectangle. So let's say we take I don't know, for the picture, I'll just do a left endpoint here. Because that left endpoint is f of x, all right? So I'm going to cut off that rectangle right there. That distance there is f of x, right? Because it's f at this point, the left end point of our interval. We can approximate that area by the area of that rectangle, okay? So this is going to be a limit as delta x approaches 0 of approximately, all right, let's put in approximately here. Oh, actually, hang on. Here's what I want to say. The 1 over delta x times this integral, this is approximately area of the rectangle divided by its width. So that would equal the height, which we already know equals f of x. Okay, because this is the width right here. The delta x is the width, right? So if we have the integral, which is approximately the area, divided by the width delta x, then that's the height. So we're then taking the limit of area divided by width. And as we take a limit as delta x approaches 0, the approximation aspect of this is going to get better and better and better, right? Because the like difference between the actual area and the area of the rectangle that we're using to approximate it is going to get smaller and smaller as delta x approaches 0. All right. So so that's going to close down, and then the approximation here that this is approximately equal to f of x is just going to get better and better and better and better until it's perfect. When we actually do the limit as delta x approaches 0, this is exactly equal to f of x, and there's no approximation about it at all. So this all boils down to this, which is what we were, what we were trying to show. It all comes from area divided by width equals height. That's basically the crux of it. And you just got to put all the right pieces in the right places and understand what is what, and that's how we get it that it's just f of x.